In this video, we'll review the use of curved arrow notation to work in reaction mechanism. I'm going to go through these 4 examples. As we go through these examples, you'll see that it'll be useful to keep in mind that essentially curved arrows are going to represent 3 different kinds of changes. One possibility is a bond between 2 atoms now becomes a bond between 2 different atoms. So we can refer to this as bond to bond. Another possibility is that a bond becomes a lone pair of electrons associated with a particular atom. So this would be bond to lone pair. And the third possibility is a lone pair of electrons associated with an atom now will be forming a bond to another atom. So lone pair to bond. If we look at our example A, initially a pi bond is now going to be making a new bond to a hydrogen. So this would be an example of a bond to bond. The hydrogen that's currently bonded to the chlorine, well, that pair of electrons will now be associated exclusively with just the chlorine. So that would be an example of a bond to lone pair. If we go to predict the products, I'm going to draw my 4-carbon chain. And now my pi bond is making a bond to a hydrogen. I'm going to arbitrarily choose the upper carbon of the pi bond, but that new bond to a hydrogen could occur to either of those 2 carbons. Note that there is already a bond to a hydrogen at that upper carbon. So now that carbon is making 2 bonds to hydrogen. The other outcome here is chlorine has been released, and because the pair of electrons that originally was being bonded between the chlorine and the hydrogen is now associated exclusively with that chlorine will have a negative formal charge. Now, the other thing to keep in mind when we're thinking about reaction mechanism is if overall a set of reactants are neutral, well then the products will overall need to be neutral. So this alerts us that there must be a positive formal charge, and that's associated with this carbon right here. Now originally, and I'm just going to use my arrow here pointing, and let me just change the color so we don't get confused. So originally this bottom carbon is part of the carbon-carbon pi bond. That carbon would be neutral. It is making a total of 4 bonds. It owns half of the electrons in those 4 bonds. Normally, carbon would have 4 electrons in the neutral state. Therefore, that carbon that I'm pointing to in green is neutral. The carbon in our product here is making 3 bonds, 3 sigma bonds. Normally, carbon to be neutral would be making 4 bonds, or would own 4 electrons. So in this case, this carbon is only owning 3 electrons in making those 3 bonds. Therefore, it have a positive formal charge. Anytime that carbon is not making 4 bonds, whether in a carbocation or a carboanion, and it's making 3 bonds, it will have a charge. Looking at our next example, we can see that a pair of electrons is now going to be making a new bond to a carbon. So this would be an example of a lone pair to bond. We also see a pair of electrons now becoming associated with only the bromine. So this would be a bond to lone pair. In terms of predicting the product, I'm going to write everything intact that doesn't change. And now the lone pair that belonged to this carb anion is making a new bond to a CH3 group. And I can show the entire CH3 group, or I could also draw it as a bond line drawing. The bromide has been released, negatively charged, because the pair of electrons that was being used to bond to the carbon is now exclusively associated with that bromine. Note, overall on the left-hand side, we have a negative formal charge, and overall on the right-hand side, we have a negative formal charge. Let's now look at the next example. The oxygen as part of the alcohol group is now going to use a lone pair of electrons and make a new bond to this carbonyl carbon. So this would be an example of a lone pair to bond. We can also see that a pair of electrons involved in the pi bond in the carbonyl will now become exclusively associated with the oxygen in the carbonyl. So this would be an example of a bond to lone pair. In terms of predicting the products, I'm going to draw in everything that doesn't get changed. I'm now going to draw my bond to the oxygen. And because of the pair of electrons involved in the pi bond is now exclusively associated with the oxygen has a negative formal charge. What used to be the carbonyl carbon is now making a bond to what used to be the alcohol oxygen. The alcohol oxygen still making a bond to a hydrogen and to a carbon which is bonded to another carbon. Now you can see that the oxygen right here that used to be the carbonyl oxygen has a negative charge. On the left-hand side, everything's neutral. This alerts us to the fact that we have another formal charge in our product. The formal charge is associated with the oxygen. This oxygen is making 3 bonds. Normally, neutral oxygen's only making 2 bonds. We can write in an extra lone pair of electrons, and if we assess the formal charge, this oxygen only owns 5 electrons. To be neutral, oxygen needs to own 6 electrons. So there's a positive formal charge. That would be our product. Now, if you take a peek down to the example D, you can see that what we drew for our product in C is actually our starting reactant in D. So this is a sequence of reaction steps. So now labeling the curved arrows, I can see that the oxygen's lone pair of electrons is now going to become a bond. So this would be an example of lone pair to bond. And at the bottom here, we have the pair of electrons between the carbon and the chlorine now becoming exclusively associated with the chlorine. So that would be an example of a bond to lone pair. The outcome of this step will be, and note, I'm going to make sure that I keep everything intact that doesn't get changed. And so I still have my oxygen making a bond to a carbon and a CH3. That oxygen is making a bond to a hydrogen. It still has a positive formal charge. The other oxygen is now making yet again a pi bond, so it's in the form of a carbonyl, and I have my chloride. Now note, on the left-hand side, we have overall a neutral charge, because we have a negative and a positive, and on the right-hand side, overall, we have a neutral charge. I hope this short video has helped you review a bit the idea of curved arrow and reaction mechanism.